Okay, today we're going to Simulink and Math as I promised you. I'm going to share after class with you and about the second order system, and I told you, now you're expert of that the closed loop transfer function is omega n square in s square plus 2 zeta omega ns plus omega n square. And I told you when it comes to Simulink, you have to find what? Open loop transfer function, G1 plus G, and I told you that G is obviously omega n square s square plus 2 zeta omega n s. Being said, in the Simulink, your num is 0, 0 second order system and omega n square, and the then is what? 1, 2 zeta omega n and 0 here for open loop transfer function. Why? Because in the Simulink, as you're going to see, like as the first order system, right? Here you have G, right? And this is Y. And the unity feedback, assuming that the sensor is ideal, so transfer function is 1. You got it, everybody? Well, when it comes to the MATLAB, I'm going to do also today, you have to use what? Closed loop transfer function for the coding. So num is the same as I wrote above, 0, 0 omega n square, but then is different. That's right. 1, 2 zeta omega n and omega n square. There we go. You got it? So in the Simulink, I want to say, I'm going to say that the input of the system is the unit step, and the input to the system I'm gonna is what? Is ramp. So let's do it together. And I'm then gonna back about the transient response and the steady state response of the second order system after this. So I have it here ready. I have to just open from previous class first order system to save time. And again, I'm going to share this with you after the class by emails. Bear with me. Until it comes up, maybe you want to write it down. So, okay. So I'm going to say, oh, okay, there we go. Oh, what's happening here? Okay. Okay, good. So I'm going to copy and paste this one, because the body of the second order system I'm going to later. So I'm going to put a new, I'm going to paste it here, and then I'm going to save it as M530 on the second order system. Oh, I'm sorry. Second order system. And what I have to do, I have to, this is the step, I'm just opening to make sure that there's no delay on that. 0, 1 unit step, and I have to change this. And the num, as I said, is 0, 0, and I assume that omega n is 1, just a number, huh? And I'm gonna do for underdamped system. So I'm gonna say, I'm writing here, guys, for you. for underdamped system, I'm gonna say zeta. What happens? Hold on. I'm gonna say okay. I'm gonna say zeta. Two cases. Underdamped system is 0.2 because it's smaller than 1, remember? And then I'm gonna plot for critically damped system, and then I'm gonna plot for overdamped system. I'm gonna say zeta is 2 for unit step. And as I said, just a number, number is I say omega n is 1 radian per second, and then as you know, there is no unit for the damping ratio. Okay, so what I'm gonna do, I'm gonna move this. What is this? Oh, this is first order system. I don't want to work with the second order system. Okay, I'm gonna move this to this side. I'm gonna first let's fix it. So underdamped system 1, 2 zeta is 0.1 in omega n is 1 and omega n square is 1. I'm sorry, 0 here must be for the Simulink. Okay, open loop transfer function, and here we go. 2 zeta omega n and 0 0 0 1. Okay, now I have that. I'm gonna copy and paste here. Only I'm gonna change the zeta value. Zeta value for critical damped system is 1. Here we go. And I'm gonna again paste like here, Control V, and I'm gonna put this as zeta is 2 overdamped system. Sorry, this is 2 overdamped system. Okay, here we go. Okay, and for God's sake, I'm gonna remove all of these. Let me do like that. Okay. Here we go. I don't need this. I'm gonna compare all of that together. I don't need this. Okay, and I'm gonna bring this down here. Oh, okay, let me keep like that. Okay. Okay, I'm gonna say 1, 2, 3, 4 inputs. There we go. So I'm gonna connect this critically damped and overdamped system. And for making this beautiful, I'm gonna move it here like that. Okay, and the error signals, I'm gonna do the same. I'm gonna put a max here, copy and paste, and we have 3 error signals. 3. Here we go. And I'm gonna copy and paste this here. Here we go. And I'm gonna delete this and sorry. The first error signal, the second error signal, and the third error signal for the overdamped system. And I'm gonna erase this. I don't want those. Here we go. So as you know, you can write here as here we go. This is so I now can run it for 10 seconds. If I run it, here we go. This is the output I'm plotting here. Oh, I need more time. Say 20. Okay. Run it. Here we go. So the blue line is what is unit step input. This is input. The yellow is for the underdamped system. This orange is for the critically damped system. And as I promised you, the green is for the overdamped system and takes longer time to go to origin. But because I selected a very low amount of number, let me increase it a little more. I'm going to put as 0.5. It still is smaller than 1 on the damped system. So if I now plot, oh, I'm sorry, I plot. Here we go. See, oscillation and vanishes, goes to the final value, critical damped system, overdamped system, and finally goes to 1 all of them, as we did. Okay, and I promised you that we have an overshoot here, a maximum peak. I'm going to talk about this, and the settling time. These are settling times here. I'm going to talk about those because we're going to design controller based on this. So obviously the error signals goes to 0 finally. See, 0 for 3 cases. You got it, everybody? Now I'm going to copy this, going to put here for the input of the ramp. There we go. Just make sure that there's no delay. Yeah, it's good. For underdamp, I'm gonna just decrease it again to 0.1 to make it sensible. There we go. Ooh. Okay. Now if I run that for 10 seconds. See, this is the ramp input and it's oscillating for the output. If I increase that to 25, there we go. See, and finally converges to that. If I increase it a little more to make it sensible, again 0.5. So I want to show this. Do you see? This is 2 zeta over omega n. This error signal, guys, as we derive. And you have oscillation kind of here. See, this is the oscillation and comes here. This is the oscillation. Let me magnify it for you. See, this is kind of oscillation. Okay, but you have 2 zeta over 2 zeta is I selected is 0.4, right? Over n. So it's going to be 2 zeta over omega as we calculated error signal. And this is the error signal, see? And you have a, here we go, 1. 2 zeta, 0.5, 2 by 0.5, 1. Omega n was 1. This is the steady state error signal you have. So you have to fix it by designing the PID controller. You have to make this to 0, finally. Now, as homework, when I'm sharing this with you, please at home, do the Simulink for the input of the impulse. You know how to do it by derivation of the step input. And parabolic, you know how to do it. I taught you as homework for yourself. You got it? But, yes, okay. But when it comes to the MATLAB, just quickly, you know how to do that, right? Let's see, CLC, clear all, close all, and the num, okay, 4. I'm going to put in a for loop. For zeta is 0.5 and 5 until 1.5. Oh, let me do this. 0.2, 0.3 to 2. From very underdamped to overdamped. Okay, I'm gonna say num is the same. Num doesn't change. Num equals to 0, 0, 1, as I said. But then I'm writing like this: 1, 2, zeta. Okay, zeta in omega n. Let me put omega n. I write like this. Maybe you can change it and play with that at all. Omega n square to zeta omega n. And now for the MATLAB, you have to use what? Closed loop transfer function. Here is not 0 like Simulink. Here is the value, right? So then, and then I'm gonna say figure 1. Figure 1. Figure 1. I'm gonna say step num and then and then I'm say hold on, then end. You got it? You can write like this. And then this is coding of second order. You got it? If I run this, oh, 0. So yes. Here we go. Do you see that? Simple like this. Step response is plotted under damped, and when you increase the damping, you see that the maximum overshooting decreases, and eventually critically damped, and finally overdamped. Can plot it for you, obviously, and you can just play with that after graduation. Oh my god. Okay, you can say obviously grid, right? There we go. Here we go. You have it. Okay. How to plot the because we don't have ramp. I taught you how to do it as homework. Use this code, change the num and then, and plot the what? Plot the ramp input. Okay. Use this code. Okay. Now we know it. Now we know everything. Oh no. Okay. So now let's go back to the notes. So, you saw, as I promised in the previous class, like as your car cruise system, you want to go from, I don't know, 20 to 70, 60 mile per hour. Or for your car suspension system, that after passing the bump, you want to settle down. So in the most cases, you're going to have, except the robotics case that your friend asked me, you want to have such an underdamped response. This is exactly your car, guys. Exactly your car. After passing the bump, see. Okay? Settles down, okay? So even after passing a step profile in the road. As I told you, we have two parameters that we are designing controller based on this. One of them is MP, maximum peak or overshoot. Maximum peak or overshoot. And this is for transient response. Transient response. Transient response. I'm just showing you, not teaching you now, just telling you. If you want to fix or modify transient response in control after graduation, you have to design PD controller. PD controller. Proportional derivative. I'm going to teach you later. But if you want to fix steady state response, we are named because steady state means that this oscillation vanishes. Steady state, we are saying steady state. Like what? Like ESS. Remember, steady state error signal. You want to make it 0. You have to design. This is function of I controller. I controller. How? I'm going to teach you later after the midterm. You got it, everyone? So, but you see that after the first pick, you have a second pick, and you have third pick here. These have names. We named as TS in 5% criteria and the TS 2% criteria. Means this pick is 5% of what? The first pick. This pick is 2% of that. And TS name is settling times, as I told you. Settling time. Settling time. So we have to play with this when designing controller. I'm going to teach you now by mathematics. Okay. So, guys, from algebra from high school, what is 0 here? You tell me. This is not control, this is not vibration, this is not robotics. This is high school. I'm asking you mathematical questions. What is 0 here? Huh? This is high school. In this profile, what is 0 here? Slope. Yeah, exactly. Derivative slope is here is 0. So when you have y of t from the previous notes for the underdamped system, second order, it was like this. You having a note zeta omega and t cosine omega dt plus zeta over 1 minus zeta square sine omega dt. If you want to find the maximum peak, you have to say dy. This is because this is y versus time t. dy over dt is 0. I have taught this in the vibration class in the previous semester. I don't want to repeat because here's the control. I'm skipping the math. If you do that and then replace there, okay, you get that maximum peak in percentage is E minus zeta pi divided by 1 minus zeta square. I'm teaching from my mind. I hope I'm right. Okay, this is like that. So it says the maximum peak is only function of time. It's only it's only function of damping ratio. Zeta is only function of damping ratio. So MP is a function of damping ratio. I'm getting older. What I'm doing today. So here we go. Damping ratio. That's why in the MATLAB coding and simulating, you saw that when I was decreasing the damping ratio to very underdamped, you had a huge what? You had a huge overshoot. When I was increasing that to the border of decreasing damp system to 1, it was decreasing. You got it? And then we have 2 settling time. TS in 5% criteria. I derived this already in vibration, but this is control. We're gonna design control, not vibration class. It's 3 over zeta omega n for the second order system. These are formulas. and the settling time at 2% criteria is 4 over zeta omega. And you're gonna tell me, okay, so what? What do I have to do with this? Can I go to the next page? Yes, everybody? I told you that the underdamped system like this has what kind of the poles? All of you look at your notes. I taught you, we did together. What kind of the poles has underdamped system? Yes, name of that is a pair of complex conjugate poles. Remember? A pair of complex conjugate poles. And they were like this, P1 and 2, that the roots of the denominator was minus zeta omega n plus minus I omega d, right? And you saw in the mathematics and simulate, this leads you to this profile for step function, right? Now, you boss says, you're working in a car industry, says, you know what, Mike, you know, now what, Elizabeth, I want that you design a car suspension system for me that is underdamped and has a pair of complex conjugate poles like this, and has, I'm so sorry, and has maximum overshoot off underdamped, as you're experiencing every day by your car, 25%, and settling time of typically for your car after passing a bump or step profile in the road is say 2 seconds. Huh? So now you have to go reverse engineering. You're gonna say, okay, I got it. 25% means this is minus zeta pi. I'm gonna do right now with you. Minus zeta square. 2 seconds. You're gonna say which criteria? It's gonna say criteria of 5%. You're gonna come back to your notes, say, okay, that's the formula. I got it. So it's gonna be 2 seconds, gonna be 3 over zeta omega. Now from these equations, you have to find zeta and you have to find omega. Let's do that together. Suppose that I'm teaching you the control from now eventually. But I know that this area of the coding and MATLAB. I close MATLAB? Okay. So you come here and say like this. Very nice. You come here and you develop a simple code here. You don't need to even to write everything. You're gonna say, come on. Oh no, clear all. You're gonna say sims x. Your unknown zeta is x, for example. Symbolic definition of the x. And you're gonna say zeta equals to solve command in MATLAB, and you're gonna write the equation. The equation is this side minus this side is 0. So you're gonna say exponential of minus x multiplied by pi Okay, there we go. Divided by SQRT of 1 minus x to the power of 2. Here we go. Exactly, you see, I'm typing this here. Minus 0.25. Sorry, guys. Here we go. Minus 0.25, 25% of the overshoot. And I'm gonna say eval. Give me the numbers. Okay, I'm gonna save this as zeta omega n solution. Okay, now I'm gonna do first debug it. Okay, it gives two roots. One of them is 0.4, which is under damped system. Obviously it is good, but this is not acceptable because we don't have negative damping ratio. When you have it, it's very simple. Use this formula. Omega n is 2 zeta divided by 3. So you say natural frequency is 2 zeta divided by 3. Let me do that. Okay, see here? 2 zeta divided by, oh, sorry, 3 divided by 2 zeta. I'm getting over. 3 by, there we go. 3 divided by this. We got it. So let me double check everything. I want to make sure minus zeta pi divided by sqrt 1 minus zeta squared. I want to make sure that all brackets still right. Minus 0.5. Here we go. And eval. And this 3 divided by 2. Okay. Here we go. We got it. So it says, I'm writing here. It says, can you please read this? Can you please read this number for me? Please write in your notes and read for me, okay? Because I want to do it here. 0.4037, 3.41. Did you write it, everybody? Yes?
Yes.
Okay, so bear with me. I'm gonna say, oh my God. Okay, read for me. From this equation, oh, what's happening here? Okay, from these equations, we got zeta how much? How much? 0.4 and omega n 155 radian per second. When your boss says, I want to have a suspension system of your car, a spring and damper, it has a maximum overshoot of 25% and settling time of 5% is 2 seconds, it means that your zeta must be this and omega is this. Bear with me. Okay, so this gives you the poles of the system. Poles of the system is this 0.437 multiplied by obviously minus 3.7155. It's real part plus minus I omega d is omega n 3.7155 1 minus 0.037. This is imaginary part. Let's do that together, because eventually I'm going to teach you how to design control for these poles. Okay, so you come here and say real part is zeta omega n, and imaginary part, let me say part, is omega n multiplied by SQ RT of 1 minus zeta square. There we go. You got it? Actually, zeta 1 and 1, because see first row and second, and that's why I'm doing like that. Okay. So let me put a pause here to make sure that I'm doing correct. Okay, omega n is right, and here also I have to do this. Zeta 1 and 1, the positive one. Zeta 1 and 1 square. Okay, and we don't need this. I'm writing here. So we have real and imaginary parts of poles yielding 25% overshoot and settling time of 2 seconds for your car suspension system. This is comment. You got it, everybody? Now let's see the values. So real part of your pole is gonna be 1.5. Imaginary is 3.3993. So I'm gonna write it down here. 3.3993. Okay. Let's go back to the next. So the poles of the system, based on the request of your boss, is minus 1.5 plus minus I 3.3993. Am I right about the numbers? Yes? 3.993. Here we go. Okay, guys. I told you car suspension system. Exactly, if you go over the tire of your car, the new cars, there's a damper and there's a spring. And this is the wheel of your car. Huh? You get it? And this is mass of your car, say. I'm just simplifying. Maybe already your car poles are this. Minus 0.5 plus minus I. The original one is this. But you want to design a controller that push here. How are we going to do this? By PD controller. The original one is this. That we name it active suspension system. Okay. We're going to use by, this is new that you want to have, desirable. This is old. Okay. You get it? Now, if you want to see the difference between them, it's okay. I'm gonna do that for you guys. Yeah. Just put here S square plus 2 zeta omega ns plus omega n square in the Simulink or MATLAB. Look at here, guys. Okay, so I'm gonna do that here. Okay, I'm gonna develop the code. I'm developing the code. I'm saying num 0 0 omega n square, second order system. Then, as we calculated from your bus request, 1 2 zeta 1 and 1 in omega n, we just calculated, and omega n square. Figure 1, step, num then grid So you see that this is a zeta, guys, and this is like this. Okay? You see that this is a step response based on your bus request for MP and TS. Okay, let us examine that, guys. Here we go. Exactly 25% overshoot, 1.25. Here we go. Minus 1 is 25 overshoot. Settling time was how much? Settling time? 2 seconds. Yeah, almost 2 seconds, not exactly. But it's good. See? It's good. Acceptable. So your boss says, hey, I have electromechanical system and I want to have maximum overshoot of 15% and a settling time of 6 seconds. You have to go back this way to drive your pulse. Once you have the pulse, desirable pulse, I'm gonna teach you how to design controller to push system toward that pulse. You got it, everybody? Yes? Clear? Yes. No, 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 no. I said that your boss says design this second order system. We have the car suspension system here, okay? That has maximum overshoot of 25%. Your boss asks from you, okay? See what I'm saying? Your boss, the boss that paying you money, salary, okay? Telling you that, hey, Mike, go and design a control system that gives to me maximum 25%. Maximum, this must be 25%, or 0.25. And the settling time is 2 seconds. Settles after 2 seconds almost. See what I'm saying? These are the requests. They are hiring you as control engineer, paying you salary and paycheck every month, and giving you this and asking you go and find these poles for me. See what I'm saying? No. Here. Yeah, exactly. Oh, you mean this? How to solve the, oh, this is the command. Okay, good for asking.
Making sure that's what we're basically
Yeah,
solving.
yeah. So hold on. So the MATLAB, if you want to solve this equation, forget about that, okay? Plus cosine x equals to 0.3. Huh? This is the equation, right? Huh? MATLAB, you have to say, I have to define sims x. You have to define it as symbolic, sims. This is a command in MATLAB. Let me change the color. Sims x means this symbolic. Then you have to say solve, and you have to change this to this x squared plus x sine x plus cosine x minus 0.3 equal to 0. You have to just type here. This is MATLAB, how we write in MATLAB. X squared plus x star means multiply sine of x plus cosine of x minus 0.3. This is gonna solve the problem for you. You got it? So now exactly here. This is the equation. You got it? I just typed this minus 0.25. I'm taking to the other hand, to other side. You got it? So instead of zeta being said, instead of zeta, I'm defining zeta as x. Solve exponential of minus x pi means zeta pi divided by root square of 1 minus zeta square minus 0.25. You got it? Now, if your boss says, you know what, Elizabeth, this time I want to have maximum overshoot of 12%, means 0.012. See what I'm saying? This time,
Yes.
if I do that, see? Oh, 12%. This is different. See that? Okay? This is 12%. There we go. If you want to zoom in, see? Almost 1.1 and almost 1.2, the maximum is. 12%. See, exactly 12. 1.12 minus 1 is 0.12. See what is happening? So by this code, you can just change the parameter that the boss asks you, and you can, and for that, you have to have the, let me teach you. Let me rerun it. Okay, your damping gonna be this time 0.5594 under damp system, and oh, this must be 2, guys, this time, because this is near 2, zeta 2, and zeta 2. Okay, let me run it. You have to check your answers. Here we go. Zeta is this. Oh, 2, 1. I'm sorry, guys. It's two rows, 1 column. 2 rows, 1 column. 2 rows, 1 column. Okay. There we go. Okay. Now we have your zeta is this 0.5594 under damp. Your natural frequency based on that gonna be 2.068 radian per second. Real part of pole is gonna be minus 1.5, and imaginary part is 2.55. So it's gonna give you, and also this must be 2.1. Anywhere I have to divide everything. Here we go. Real part is 1.5, imaginary part is this, and this is exactly what you have. You got it? Okay. I'm gonna share this code and the Simulink file to you. Next class, now you know what the rule of the poles on the system. I'm gonna teach you dominant poles. Dominant poles. Now you know how a system works, that's right? How we solve in MATLAB. Guys, everything is not second order system. If you pass vibration with me, you know that. Let me give you an introduction to this. You know that this system, mass spring dampers, say this, a damper here, a mass here, a damper here, sorry, a spring here, another mass here, and a damper here. I'm gonna say K1, C1, K2, C2. This is the mass M1, mass M2, and we are applying two forces, F1, F2. For God's sake. Okay, let me derive the. I just want to skip how I derive it because this is vibration class topic. But now we have to be expert of that. This is gonna be K1, K2 because when you have two forces, you have two displacement, X1 and the X2. And you know that two masses, two independent motion. We name it the 2-degree of freedom system. What are the degree of freedom system? X1 and the X2. So I have to erase this, guys. C1 X dot 1 plus K1 plus K2 in X1 minus K2 in X2 is equal to F1. I'm going to work on this in the next class. Write it down. M2 X double dot 2. And where is it coming from? From ME220 that you passed in San Diego State. Dynamic course. Sum of the forces in X direction is mx double dot Newton's second law. May you have seen this in high school even. Plus C2 X dot 2 plus K2 X2 minus K2 X1 is equal to F2. This is, if I tell you, hey, guys, find me the closed loop transfer function of x2 over f2. I'm gonna do the next class. I bet that it's gonna be fourth order system, like as a s4 plus b s cube plus c s square plus ds plus e. I'm going to calculate this fourth order system. Saying that, how many poles we're going to have for fourth order equation from high school? How many poles we're going to have? For second order, we have 2. For 4, we're going to have 4. P1, P2, P3, P4. So now this becomes complicated. That's why I have to teach you dominant poles on the system. Which poles are dominant? Which poles are weaker and we can eliminate their effects from the system? Okay? You got it, everybody? Yes? Good, guys. So, see you next class. Thank you, everybody.